Are you ready for circuits? Let me tell you that this is the most important chapter in this semester. If you're ever going to see something again in your future career, whether it be engineering or medical science, you're going to see something dealing with DC circuits, because even the human body is the nervous system of the human body is a DC circuit. So, very important that you master this stuff, and it's pretty logical, straightforward stuff. So hopefully you can master it very well. A word about the electromotive force, or EMF, represented by the symbol epsilon. That is the impetus to cause charges to move in a circuit. Basically, it is the voltage of the battery. Strictly speaking, it is the voltage of the battery before considering the internal resistance of the battery. But for our purposes, we're going to ignore the internal resistance of the battery, and we're going to treat the electromotive force, epsilon, as simply being the voltage of the battery. So for our purposes, it is the voltage of the battery. It is the potential hill that is established that allows positive charges to move down the hill to the bottom of the hill, which is the negative terminal. So, all things said, the EMF, epsilon, is the voltage. Here are two laws that are used very often. Ohms Law, V equals IR. Here's a mnemonic device that somebody in the military showed me. The way you would use this device, this memory device, is you would say V is equal to I times R, or you would say a current is equal to voltage divided by R, or you would say resistance is voltage divided by current. Or you can just look at this simple algebraic relationship and solve for the unknown, which is probably what you need to do. But sometimes mnemonic devices help pretty well. Here's one for power. Power is equal to current times voltage. And here's the mnemonic device for that as well. So if it works, use it. That's my theory. For a series combination of resistors, if resistors are connected in series, they're along the same line of the current, and there's no other connections possible. So whatever current, whatever charge per time is flowing through one resistor has to flow through the next resistor and the next one after that. In series, that means they must have the same current. There's no other possibility, no other flow into that series combination. Hence, if we had a series combination of resistors, the same current will flow through each one, and that means the same current will flow out of the battery in this configuration as might flow in an equivalent configuration. In other words, as far as the battery is concerned, the same current is flowing out of it. It doesn't know what's going on with any equivalent circuit because they are truly equivalent. So the same current will flow out of the battery in this equivalent circuit as what flows out of the battery in this original circuit. Hence, I equivalent is equal to I1 is equal to I2. If we use voltage addition, as we go down a voltage drop across resistor 1 and then a voltage drop across resistor 2, we will do the full potential hill provided by the battery. Hence, that would be the same potential as it is across our equivalent circuit, our equivalent resistance. So we could say that that voltage of the battery V is equal to V1 plus V2. Using the definition of Ohm's law, we would then have that the current times R equivalent is equal to the current times R1 plus the current times R2. Since I is the same in all these terms, and it's the same on either side of the equal sign, we can divide through by I and get rid of that, and we get this result. R equivalent is equal to R1 plus R2. We did this for two resistors in series, but we could have done this for any number of resistors in series. Resistors in series add, and that gives us our total resistance. It kind of makes sense intuitively. If I were an electron traveling through this wire, and I encountered a resistor, I would encounter resistance. And then there was another resistor, I would encounter resistance with that. So the total resistance would just simply add as I encountered resistance along the way. Kind of makes sense. If I have a parallel combination, it must be true that things in parallel have the same voltage. So if I had a battery connected in parallel with R1 and R2, both R1 and R2 will have the same voltage of the battery. And that would be the same as if I had an equivalent resistance that represented this parallel combination, because that's going to be across the same battery. So the voltage across the equivalent will be the same as V1, will be the same as V2, or any other resistors in parallel. It should have no different effect on the battery. Battery shouldn't know any difference, and hence the voltage will be the same. Now if I had a current coming out of the battery, that current will be the same as well. No difference as far as the battery is concerned. So in my first setup, I have I coming out of the battery, but that current's going to have to split when it reaches this junction going into R1 and R2. So I equivalent is going to equal I1 plus I2. We have to have charge conservation. So whatever current flows into a junction must equal the current flowing out of that junction. That is still the same current flowing in our equivalent circuit, which is totally going through our equivalent. So we must have that I equivalent is equal to I1 plus I2. Now using our definition from Ohm's Law, since V equals IR, I is equal to V divided by R, and hence we have that the voltage of the battery divided by R equivalent is equal to V over R1 plus V over R2. But these voltages are all the same, and we have the same voltage on either side of the equal sign, so we can divide through by our V and get rid of our voltage, and we're left with this. 1 over R equivalent is equal to 1 over R1 plus 1 over R2. We do this for two resistors in parallel, but we could have done this for any number of resistors in parallel. 1 over R equivalent would equal 1 over R1 plus 1 over R2 plus 1 over R3, as many resistors that we had in parallel. So for a parallel combination of resistors, that's how we do it for any number of resistors in parallel. In the particular case where I had only two resistors in parallel, note the following. 1 over R equivalent is equal to 1 over R1 plus 1 over R2. I want to find a common denominator for these two fractions on the right, so I'm going to multiply them both by 1 and get a common denominator. So this is equal to R1 plus R2 divided by R1 times R2. If I flip both sides of the equals, I get that my R equivalent is equal to R1 times R2 over R1 plus R2. My R equivalent for two resistors in parallel is equal to the product over the sum. That's only true for two resistors in parallel. You can't do it for three. You can prove it to yourself by trying to do the math. Finding a common denominator, it won't work for three. So it's only for two resistors in parallel that the equivalent resistance is the product over the sum. But if you had a bunch of resistors in parallel, you could do them 2 by 2 by 2 by 2, product over the sum, product over the sum, product over the sum. Start simplifying it down to lesser and lesser resistors, always doing 2 by 2 by 2, product over the sum, and you can reduce the parallel combination that way, and that will work. So you can always take them 2 by 2 and reduce it down that way. Notice that this result and the result for resistors in parallel is the same mathematically as capacitors in series. And capacitors in parallel is the same mathematically as resistors in series. So we have the same kind of formulas, only they're reversed as far as series and parallel between resistors and capacitors. Note also this, that the equivalent resistance of any parallel combination is always less than any individual resistance in that combination. How can we prove this? Well, let R1 be any individual resistance in the combination, and let R2 be the resistance of everything else. So we're going to have our particular resistor, R1, in parallel with everything else, whatever that configuration might be. So if we were to calculate the equivalent resistance of that, it would be product over the sum, and we would, factoring out our R1, we have R1 times this fraction, R2 divided by R1 plus R2. This fraction will always be dominated by 1. It can never be greater than 1, and at best, if R2 were infinitely large, it would be equal to 1. But it's always going to be dominated by 1, which means that our R equivalent will never be greater than R1, any particular resistor that we have in the combination, and most likely will be less than that resistance. What does this mean? Well, if I had 5 resistors, like you have in lab maybe, that the equivalent resistance of those 5 will always be less than the smallest resistor in that combination. If I had 2 mega ohms in parallel with 200,000 ohms, in parallel with 150,000 ohms, in parallel with 1,000 ohms, the equivalent resistance of that parallel combination will be less than the 1,000 ohms. Why is this true? Well, if I were an electron and I were encountering 1,000 ohms and I had to go through there, that would be the resistance I would encounter. But if I had any other options, if I had other parallel options, then that should reduce my resistance. In other words, say for example you're driving down the road and you have only one lane to go through, so you have a particular resistance in trying to get through that lane. But if you have other lanes that open up, no matter how dense the traffic is, that still is going to reduce your resistance as far as trying to get through that superhighway because you have more options. And if you give yourself more options, then your resistance is going to be reduced. In the special case, where we have n equal resistors in parallel, then R 1 over R equivalent is going to equal 1 over R plus 1 over R plus 1 over R plus 1 over R n times. So 1 over R equivalent will equal n times 1 over R. I could algebraically solve for R equivalent or just flip both sides, and I would have that R equivalent is equal to R divided by n. So if I had 5 2 ohm resistors in parallel, the equivalent resistance of that would be 2 divided by 5, or 0.4 ohms. You might say, well, how often am I going to have parallel combinations of equal resistors? It actually comes up a lot more often than you might think. So this could be a nice little handy formula to have ready to go. Let's try out our newfound tools on a circuit. We have a network of resistors here, and we're going to connect it across an 18-volt battery. And our question is, find the current in the 12-ohm resistor of this circuit. What we're going to use is our series parallel formula, and we're going to use the fact that things in series have the same current, and things in parallel have the same voltage. So first thing we're going to do is find the equivalent resistance of this network of this circuit. To do that, we might notice that none of these resistors are in particular in series with any other resistor. So we're going to have to start with our parallel combinations, and we have a 6 in parallel with the 6 and a 4 in parallel with the 12. Since there's only 2 of them, we can use that product over the sum formula. And so for the 6 in parallel with the 6, I'm going to have product over the sum, 6 times 6, 36, over the sum, 6 plus 6, 12. 36 divided by 12 will 12 will be 3. So the equivalent resistance of this parallel combination will be 3. And with the 4 and the 12, I'll have 4 times 12, 48, over 4 plus 12, 16. 48 divided by 16 is 3 as well. So my new circuit will look like this. Just substituting in for those parallel combinations, 3 and the 3, I got this. Alright, now I have series combinations, a 3 in series with a 3, and a 3 in series with a 2. To be in series, they must be along the same line and not have any other connections. So they're forced to have the same current flowing through them. I can just add my series combination. So 3 plus 3 is 6, 3 plus 2 is 5, and now my circuit looks like this. Now the 6 and the 5 are in parallel. To be in parallel, they must be connected on both ends, and they are. So I have a 6 and 5 in parallel, and there's only 2 of them, so I'm going to do product over the sum. 6 times 5 is 30, divided by 6 plus 5 is 11. 30 divided by 11 is 2.73. So my circuit looks like this. I have a 3 in series with 2.73 ohms. Since they're in series, I just add them together, and my final equivalent resistance is 5.73 ohms, and I have 18 volts connected across that. Sounds good. So that is my equivalent circuit, 18 volts connected across 5.73 ohms. Now I can find the current coming out of the battery, because I'll have the same current coming out of the battery in any representation I choose. If I choose this equivalent circuit, that current is going to be 18 volts divided by 5.73 ohms. So my current coming out of the battery is 18 divided by 5.73, 3.14 amps. That's going to be my current coming out of the battery in any representation I choose, because my equivalent circuits should have no different effect on the battery. So if I look back at this previous circuit here, I'm going to have 3.14 amps coming out of the battery, going through the 3 ohms and going through the 2.73 ohms. In particular, I want to focus on this 2.73 that has 3.14 amps going through it. The voltage across that 2.73 ohms will be, by Ohm's law, its current times its resistance. V equals IR. I'm going to have 3.14 amps times the resistance 2.73 ohms, 8.57 volts across that 2.73 ohms. For that matter, the other 9.43 volts available in the circuit is going to be across the 3 ohms to the left. But right now I'm going to focus on this. I got 8.57 volts between this point in the circuit and this point in the circuit across this 2.73 ohms. Now those 2 points were represented by a parallel combination of a 6 and a 5, and things in parallel have the same voltage, and they have the same voltage as their equivalent device. So since I have 8.57 volts across the 2.73, that should be the same voltage across the 6 and the 5 as well. So the voltage across the 5 ohms is 8.57 volts. Since I know the voltage across the 5 ohms, I can find the current through the 5 ohms. By Ohm's law, that's going to be the voltage divided by the resistance. 8.57 volts divided by 5 ohms is 1.71 amps. For that matter, the current going through the 6 ohms on top is going to be the rest of the current. 3.14 minus 1.71 amps, so it's going to be 1.43 amps is going through the 6 ohms on top. The current must be conserved, but we're going to focus on this lower branch. We have 1.71 amps going through this 5 ohms. Things in series have the same current, and they have the same current as their equivalent device. So I have 1.71 amps going through the 3 ohms and the 2 ohms, which was the series combination that the 5 ohms was representing. So I have 1.71 amps in particular going through this 3 ohm resistor here. So now I know the current going through the 3 ohms. I can calculate the voltage across that 3 ohms by Ohm's law. That voltage is the current times the resistance. 1.71 amps going through 3 ohms is 5.14 volts. So I have 5.14 volts going across this 3 ohm resistance. Things in parallel have the same voltage as their equivalent device. So that must be the same voltage across the 4 and 12 that were in parallel between those same 2 points in the circuit. That means the voltage across the 12 ohm resistance must be 5.14 volts. And since I know the voltage across the 12 ohms, I can now calculate the current through that 12 ohms by Ohm's law. The current is going to equal its voltage over its resistance. 5.14 volts divided by 12 ohms, 0.429 amps. Whew. That is the current going through the 12 ohm resistor in this circuit, 0.429 amps. The only things that we used to calculate this was our series parallel formulas and the fact that things in series have the same current and things in parallel have the same voltage. Kirchhoff's rules. Some of these rules we've been using. We know that parallel branches have the same voltage. So we've been using Kirchhoff's parallel branch voltage rule. And that means if I had this configuration here, R1 and R2 would have the same voltage as this battery because they're all connected end to end all the way through. We've also been using, in a sense, Kirchhoff's current rule. Whatever current that flows into a junction must equal the current flowing out of that junction. So if I had a current flowing into this point right here, and I flowing into this point, the current must be conserved. In other words, whatever charge per time I have moving into that point must equal the total charge per time that's moving out of that point. And hence, I must equal I1 plus I2. I must have charge conservation. So I is equal to I1 plus I2 at that junction. That's called Kirchhoff's current rule. We've kind of been using that, but it's a very important rule. We're going to use that a lot when we get into our circuit analysis, especially in the next lecture. Let's combine these two ideas, though, in what we call current division. If I had a parallel combination of resistors, and I had a current coming out of the battery into this junction up top, it's going to split. Some of the current is going to go through R1, and some of the current is going to go through R2. These are in parallel, so it must be true that these voltages are equal. So I1 times R1 should equal I2 times R2. Hence, I can say that I1 is equal to R2 divided by R1 times I2. I'm going to substitute this into Kirchhoff's current rule. Since I is equal to I1 plus I2, I'm going to substitute in for I1 in terms of I2. And with a little bit of algebra, I would get these two results. I1 is equal to the opposite resistor, R2, divided by R1 plus R2 times the current flowing into that junction. And I2 is equal to the opposite resistor, R1, over R1 plus R2 times the current going into that junction. The way this will work out means that the lesser resistor will get the greater amount of current. For instance, if I had 10 amps flowing into this junction and I had a 4 ohm resistor and a 6 ohm resistor, the 4 ohms will get 6 amps of current and the 6 ohms will get 4 amps of current. Why? Because the lesser resistor presents less of an obstacle for the current to flow. Hence, it's going to grab more current than the greater resistance. So this is current division, and these are nice little formulas to have if you're analyzing the circuit. We can also have voltage division, and it kind of goes like this. If I had two resistors in series connected with a battery in series, each resistor is going to grab its fair share of that voltage. We can prove it by saying that the current coming out of the battery is the voltage divided by the total resistance of the circuit, R1 plus R2. And if I were to look at R1, the voltage across R1 will be that current times R1. And the voltage across R2, for that matter, will be the same current times R2. So if we substitute in our current into these equations, we have V1 is equal to R1 over R1 plus R2, V, and V2 is equal to R2 over R1 plus R2, V. Each voltage is going to be its fraction of the resistance times the total voltage available. For instance, if I had a 10 volt battery and I had a 4 ohm resistor and a 6 ohm resistor in series, the 4 ohms will have 4 volts across it, the 6 ohms will have 6 volts across it. Each resistor is going to grab its fractional share of the voltage available in that circuit. It's more intuitive than current division, that is voltage division. Let's try these things out in a circuit. Here's our problem. Calculate the power dissipated in each resistor in this circuit. We have an 18 volt battery, we have 4 resistors, 2 of them are in parallel, but we have a 1, 2, 3, and 4 ohm resistors. We want to calculate the power dissipated in each resistor. To find the power dissipated in each resistor, we have to find either the voltage across the resistor or the current flowing through each resistor, so we can employ our power formulas. One power formula was I squared R, the other power formula was V squared divided by R. So we need to know the voltage or the current. Let's find the input current first. Our parallel combination, we have 2 in parallel, we have a 3 and a 1. Product over the sum, 3 times 1 over 3 plus 1 is 3/4. So our parallel resistance is 0.75 ohms. We're going to replace that parallel combination with that, and now the 2 and the 0.75 and the 4 will be in series. So our equivalent resistance will be 2 plus 0.75 plus 4, or 6.75 ohms. So our total equivalent resistance of this network is 6.75 ohms. Now we calculate the current coming out of the battery. That's the voltage of the battery divided by our equivalent resistance. 18 divided by 6.75 is 2.67 amps. That is the current coming out of the battery. And since the 2 ohms and the 4 ohms are in series with the battery, they have to have that same current going through them. So now we know the current going through the 2 ohms and the 4 ohms in particular, and we can calculate the power dissipated in those 2 resistors. That's going to be I squared R, and for the 2 ohms, that's going to be 2.67 amps squared times 2 ohms is 14.2 watts. So that is the power dissipated in the 2 ohm resistor up top. And we're going to have the same current flowing through the 4 ohms. So that's going to be 2.67 amps squared times 4 ohms, 28.4 watts. So we've found the power dissipated in 2 of the resistors so far. What about the 2 resistors in parallel? Well, we know that the voltage across that parallel combination will be equal to the voltage going through that 0.75 ohms, and that's going to be 0.75 ohms times 2.67 amps, or 2 volts. And things in parallel have the same voltage as their equivalent parallel combination. So the 3 ohms is going to have 2 volts across it, and the 1 ohm is going to have 2 volts across it. So we know the voltage across these 2 resistors in parallel. We can employ our power formula for the voltage, V squared over R. For the 3 ohms, that's going to be 2 volts squared divided by 3 ohms, 1.33 watts. And for the 1 ohm, it's going to be 2 volts squared divided by 1 ohm, 4 watts. So that's the power dissipated in those 2 resistors in parallel. We could have done this by current division as well. We had 2.67 amps coming into the top junction, and it's going to split. Each current is going to grab a different fraction of the current. The smaller resistor is going to grab the greater amount of current. It's going to grab the opposite resistor, 3, divided by 3 plus 1, 4. So it's going to grab 3/4 of the current, and in the 3 ohms it's going to grab 1/4 of the current. So we're going to have that 1/4 of the current is going to go through the 3 ohms. That's going to be 0.67 amps. And 3/4 of the current is going to go through the 1 ohm. That's going to be 2 amps. Hence, by the current power formula, the 3 ohms is going to be 0.67 amps squared times 3 ohms, 1.33 watts. And the 1 ohm is going to have 2 amps squared times 1 ohm, 4 watts. So we get the same result that way by calculating the power formula that way. Note that the total dissipated power in this circuit, if we added it up for all the resistors, is going to be 14.2 plus 28.4 plus 1.33 plus 4, 48 total watts dissipated in this entire circuit. If we were to take the equivalent circuit, it should have no different effect on the battery. And so if we took the equivalent circuit with 2.67 amps going through 6.75 ohms, what would that be? 2.67 amps squared times 6.75 ohms, 48 watts. So it doesn't matter if we use the equivalent circuit or each individual resistor in the circuit. Also note that the power supplied by the battery is going to be the current going through the battery times its voltage. 2.67 times 18 volts is 48 watts. So that power supplied by the battery should equal the power dissipated in the circuit. If you were asked the question, what is the power dissipated in this entire circuit, one way you could go about that question of answering it is find the power supplied by the battery, because you can't get something for nothing. The energy per time has to come from somewhere, and it's coming from the battery. So whatever you're dissipating in the circuit is the power supplied by the battery itself, and that P equals the current times the voltage, IV. How about that? This gives you some of the techniques that you need to do some circuit analysis. But in the next video, I'm going to show you one approach to rule them all. How to look at DC circuits with one approach, no matter how many batteries you have in the circuit. We're going to look at one approach to solve all of these circuits.